Hey everybody, Mrs. Bodechon here. So today we're going to be doing a half-life lab using Skittles. So first let's talk about what half-life really is. It's a time on average that it takes for half of the atoms in a sample to decay. So we're really talking about radioactive isotopes here. So I need you to go ahead and set up this data table. You're going to do half-life trials and we're going to start at 0 and we're going to have 100 Skittles facing with the S up. You know how they have the S on one side and they're playing on the other. So the S up. And those are going to be representative of our radioactive isotope. Now we are going to shake them and pour them out. And whichever land with the S down, they have decayed and they become the daughter. So we're going to count them out. We're going to count out how many S's are up and how many S's are down for our daughters. And we're going to do this in half-life. So every time we shake it and dump it out, that is a new half-life. So set this up and let's get started. Okay, we're going to start with 100 Skittles S up, meaning they're all radioactive isotopes. Go ahead and put it in a beaker or cups, fill it out, flatten it out so you can see which ones are S ups and which ones are S down. Separate the two, pile, and then count them up for your first half-life. Every time you shake it and dump it out, that is a new half-life, and you're going to count them up every single time. Remember, S down means that it is the daughter or the ones that have decayed, and you can scoot those out of the way. You're only putting the ones that are still radioactive or the S up back in the beaker to do a second half-life. So this first one is 59 parent and 41 daughter. And this gets faster and faster because you have less and less Skittles to do over time. And I'm going to put up how many you have of each one for each half-life. This is the second half-life now. You can see we're separating them out. And we're going to have 28 parent and 72 daughter. And then we have our third half-life. We just shook it and separate them out. Notice I'm taking out all of the daughter or the S down, and I'm not putting that back in the beaker. So this one is 14 parent, 86 daughter. And it's going to get pretty fast here now, you guys. So you feel free to stop and pause so you can see that it's decreasing. We should really see that this is decreasing somewhere around half of what is left of our parent each and every time. Now continue doing this until they're all decayed. Okay, so here is our data table that is all finished and filled out. Notice we never got to 9 or 10 half-lives. We didn't need it because our radioactive isotope was decayed by then. In fact, it was decayed after 8 half-lives completely. So there's no need to go further. There's nothing left to decay. I went ahead and I made a graph for this. So you can look at it and you can see that my y-axis is the amount of parent isotope remaining, in other words, the S up. And then the bottom is the number of half-lives on our x-axis. And I just titled it Skittles Half-Life Decay, right? Because we are decaying Skittles, our make-believe radioactive isotope. Notice the trend here. Okay, so we do have a negative slope. If you look at this and you study it, it should be that every half-life, whatever you have remaining in your parent isotope, should decay by half. That's why we call it half-life. Now this is a roundabout average. This is not an exact science here, right? So if we have 100, it's not always going to be 50 on the dot. You saw that ours was 51. Pretty average though, right? In the big scheme of things. So just keep that in mind. Your graph should look like mine. Even if you do the Skittles lab all by yourself, you guys, the trend should be the same. Thank you all for watching. Bye everybody.